We have come to one of the last modules of our 12 weeks long journey in this computational electromagnetic course. The part where we are discussing some of the advanced methods like finite volume, algebraic topological methods, and the method that we are going to focus today is called as the mimetic methods, and it's one of the last methods that we are going to discuss in this course. So the method is called as mimetic method because of its mimicking character. So what it mimics is something that we will look into it. So let's look into the today's course content. So today's discussion is going to be about mimetic finite difference method, and the overview of today's lecture is going to be the introduction to mimetic method, its theoretical framework, the Maxwell equations in the framework of mimetic method, and we are going to summarize it. As I said, this method is quite advanced. It's not in general treated in depth in computational electromagnetic courses for various reasons. One of the reasons could be is the formulation itself is quite complex, the terms and terminologies are quite different, so people don't really use it in teaching computational electromagnetics. But I have promised that I wanted to teach advanced methods as a part of this coursework, so I am going to introduce this method. So I am not going to be as rigorous as I was in other methods like finite volume, finite element, and algebraic topological methods. We are going to give general overview and also look at the formulation from a very high level and see how we can model Maxwell equation in the mimetic framework. So let's look at the introduction. We looked at standard finite difference method as one of the first methods that we taught in this course, where we saw the E's grid, where we have staggered Cartesian grids where the E field and H field are separated by space and time, and we saw how this structured grid helps in modeling Maxwell equation. But we also said it's going to have a lot of other problems like the staircasing error and so on and so forth. So we discussed about this problem earlier, because when you want to capture very fine details, it's going to be prohibitively smaller refinement that one needs when you are working with a standard finite difference method, because we cannot really go and model such refined areas with standard spatial discretization. So we have to really refine it to small dx and dy if you are in a 2D, and dx, dy and dz if you are in 3D. So that being said, there is quite a lot of motivation to really look at finite difference method because it is an elegant simple formulation, but can we use finite difference method for non-Cartesian grids? So that means we are still in a hexagon grid or any kind of cubical grid, but can we go for non-Cartesian and non-orthogonal grids? So that's the main motivation. So the idea of mimetic finite difference method is that it actually mimics the continuous differential operator, and not only that, it allows the discrete approximation of PDEs possible, and it preserves the conservation laws and symmetries in the solution. So we discussed about conservation laws when we started with finite volume method. It conserves the energy and it also preserves the symmetry of the solution, and Maxwell equation is a conservation law. So one has to find mathematical models that can preserve the symmetries in the solution. So that being said, there is a lot of motivation to go for mimetic methods, and one has to really formulate the mimetic method in such a way that it can really capture the aspects of the Maxwell equation in principle, and at the same time it can have the simplicity of finite difference method. So that's going to be the aspect that we are going to look into. So let's now go into the theoretical framework. So the theory of finite difference method is something that we know from our first lecture modules. So we are going to use the same theory, but we are going to model it on non-orthogonal grids. So the discrete scalar function, so what we mean by discrete scalar function are are functions which are having only scalar values, and they are defined on the nodes, and we are going to call those space as Hn. So for now, assume that Hn is going to be the space where all the scalar quantities are going to be located. So those are going to be the nodal values here, and here we say if x, y, z are the global axis, locally inside the grid it can be x dash, y dash and z dash, and as you can see x, y and z are not orthogonal. So we can still consider them in the same manner we considered an orthogonal grid, where we can call I, j, j, k, and the next node in the x dash or x prime direction is called as I plus 1, j, k, and the one above will be called as I, j, k plus 1, and the exact diagonal node from this node will be called as I plus 1, j plus 1, k plus 1, similar to what we have done in the finite difference method. The discrete vector functions, so initially we talked about discrete scalar function, in the same sense we can talk about discrete vector functions, and these discrete vector functions are going to be analog of the continuous vector functions, and they have 3 scalar components. Similar to the discrete scalar functions, we are going to talk about discrete vector functions, and they are going to be analog of the continuous vector functions with 3 scalar components, and these 3 scalar components are ax, ay and az, and we call this discrete vector function as A, and we are going to define this A on a space which is Hn, but the mathcal symbol is used. So as you can see, the mathcal Hn is going to be the combination of scalar Hn. So I am going to call this as vector Hn, and this is as a scalar Hn. So the vector Hn is going to be the space where the discrete vector functions are located. The discrete scalar functions are going to be in the Hn. So next important aspect here is the material properties. As you have seen before, the epsilon and mu are the permittivity and permeability that we have been using, and these are the scalar functions that are going to be defined at the cell centers. So when I say cell center, these cells could be non-orthogonal grids, and the permittivity and permeability values are placed at the center of this particular cell. If you are in a 2D, you are talking about center of the surface. If you are in a 1D, you are talking about center of the edge. So the material properties are going to be defined at the cell centers, and they are going to be the scalar functions. And there are going to be 3 spaces that we are going to define, and they are going to be associated with the faces, and they are termed as Hs x prime, Hs y prime and Hs z prime. There are going to be 3 spaces that we are going to assign to the edges, so they are called as HL x prime, HL y prime and HL z prime. As you can see, S stand for faces and L stand for line or edges. So the vector functions are generally defined on nodes or edges or faces. So they are going to be defined in the space vector Hn, vector Hl and vector Hs, etc. And this is the 2D counterpart, and this is the 3D counterpart. And now when we look at the 3D counterpart, we can define the normal directions accordingly. So the normal directions are going to be the aspects that we are interested in. Similarly, in the 2D space, we are also having normal to the edges. So this is clear because we saw here, so the electric field are going to be defined along the edges. In 2D it is going to be like this, and the discrete analog of curl E is going to act on that particular discrete electric field which are defined in HL. Not only that, they are going to be orthogonal projection of E onto the direction of edge itself, and this we can see here in this figure that they are the orthogonal projection of E onto the edges itself. The discrete counterpart is going to have a coordinate invariant definition. So the coordinate invariant definition of discrete curl E is defined using the Stokes law as follows. So you have the n comma curl E, which is defined as the limit s goes to 0, that means the surface is converging to a very small area. It is going to be the closed integral over the contour, which is defined by L E dot dl divided by S. So this is going to be the way we define the coordinate invariant definition. So this is the coordinate invariant definition of curl of E. And as you can see in this expression, S is the surface spanning the closed curve L, n is a unit normal to S, and dl is a tangential vector to L with magnitude equal to the length, which is dl itself. Now we are going to see how this curl operator is going to behave. We know this from our previous lectures on algebraic topology and other methods, that it is going to take a value that is defined on the vector HL and it is going to take it to the vector HS. And this we have seen also in the algebraic topological method. This is the way we define it, and based on that we can define the values, the individual components of curl of E as RS x prime, RS y prime, RS z prime, and it is a transpose because we are talking about a column vector, and it is going to be equal to the curl of E. For a 2D case, for a simple problem that we are trying to address here, which is the transverse magnetic case, we will have RS x prime I comma j plus half is equal to, as you can see here it is j plus half, so it has to be y prime, EL z prime I comma j plus 1 minus EL z prime I comma j. This is the component of the curl, and it is very similar to dou Ez divided by dou y. So this is the first component that we are looking into. The second component will be with respect to x. So you see I plus 1, I plus half comma j. So it is the dou Ez divided by dou x component in 2D. So it is EL z prime I plus 1 comma j minus EL z prime I comma j. As you can see, what we are doing is forward differencing with respect to y prime and forward differencing with respect to x prime. So these are the forward differencing. We are going to do forward differencing for E field. So now we are going to look into the third component, which is the RS z prime component. And as you can see here, we have I plus half comma j plus half. So that means it has both the x derivative and the y derivative. And what we are seeing here is a very different expression to what we had before. Here in this expressions we had always the L component, the length component at the denominator, in the denominator, whereas here we see them on the numerator. So what we have done is we have just multiplied the appropriate L terms in the numerator, and we did the same thing at the denominator, and when you multiply Lx and Ly, what you get is a surface area, and you see here S of z prime I plus half and j plus half, this is a surface area, and the surface area is nothing but the multiplication of the appropriate Lx and Ly prime terms. And the third component is this Rs z prime component. And now what we can see is the expressions for Rs x prime and Rs y prime contains only the El z component, and that is we have seen here in the expressions. It has only the El z prime component, whereas the expression for Rs z prime contains both Ex prime, Elx prime and Ely prime. So that is something we know, this is something we expect from the Maxwell equation itself, and this fact is very much allowing us to introduce discrete analogues of the TM and TE modes. So what we are going to look at is discrete curl E component, and this discrete curl operator can be represented in the 3×3 form as follows. As you can see, the first row 2 columns and the second row 2 columns, they have 0. So the elements R13 and R31 and the elements R23 and R32 are symmetrical elements, whereas the leading terms are 0. So this is the way we are going to define the curl, discrete curl operator. Like the way we did the discrete curl E operator, we are going to talk about discrete curl B operator. However, here there will be a difference. We will include the permittivity and permeability as part of the discretization itself. That being said, we cannot separate them when the grid is so irregular and discontinuous. So the 1 by epsilon and so the permittivity and permeability will be part of the discretization itself. So we can discretize the compound operator. We call it compound operator because the permittivity and permeability, the material parameters, are going to be integral part of the curl operator itself, and we define it in this way. So we write them this way in a compact notation, and we see that the epsilon and mu are discontinuous. If the epsilon and mu are discontinuous and the grid is non-smooth, we cannot separate epsilon and mu, we cannot separate them from the curl discretization itself. So that is the reason we keep them together, and we can construct the discrete analog of full operator, the compound operator, using the discrete analog of the integral identity. So we start with the integral identity. This is from the basic vector calculus, when we have an integral over a volume A comma curl B integrated over the volume minus integrated over the volume B comma curl A dV. It is nothing but the closed integral over the closed surface that encloses that volume B cross A comma N ds. So we are talking about the normal projection of B cross A, and the surface is going to be the surface that is enclosing this volume. So if you substitute A equal to E and B equal to B in this equation, what we get is essentially the equation that will give us the discrete curl B operator, and we are going to get them through this equation, where we define the compound operator as the curl star. So this is a very compact notation that one can use. So we are now going to do the Maxwell equation. As you can see, we have not separated mu and epsilon out of the equation. We are going to keep them as an integral part of the equation itself. So this is done because when epsilon and mu are discontinuous and when the grid is non-smooth, this is the way we have to do it in order to get the discrete analogues proper. We can do the time stepping as a forward Euler method, and we can get the first curl equation as follows, where alpha 1 has to be defined. I will define it in the next slide, and we can also define the same way the second curl equation, and here we have alpha 2, and now we are going to define what is alpha 1 and alpha 2 in this equation. So E alpha 1 is equal to alpha 1 multiplied by E n plus 1 plus 1 minus alpha 1 times E n. So it is going to be some kind of an weighted averaging, and the weighting is going to be defined by alpha 1 in this case. For the second equation, it will be defined by alpha 2, and again there is going to be a weighting. Some amount of the time step n plus 1 and some amount of the time step n is going to be added in order to get the value of E alpha 1, and as you can see, the Tn is going to be the nth time step, where delta t is going to be the time discretization. one can see that it includes both the implicit and explicit formulation. If we put alpha 1 and alpha 2 is not equal to 0, we will have both the n plus 1 and n terms having, so it will become an, so both the n plus 1 and n terms will be part of the update equation for n plus 1, so it will be a implicit formulation, whereas if we put alpha 1 and alpha 2 equal to 0, both of this first terms will disappear and we will have only this term, and this will be again 1 minus 0 and 1 minus 0, so it will be just En and Bn, so then it will become an explicit method. One can also see when we do the dot product of divergence on both sides, what we get is the divergence of Bn plus 1 minus divergence of Bn is equal to 0, because this is a identity. When you have divergence of curl, the divergence of curl will always be 0. This is from vector calculus. Hence what happens is, once the divergence is satisfied for nth time step, it will be always satisfied for n plus 1 time step, and you can go on doing it recursively. So once it is satisfied for n plus 1, it will be satisfied for n plus 2, so on and so forth. So for all the time steps it is valid. So let us look at the Tm mode. What we will have is the Bs n plus 1 x prime minus Bs n x prime. This is the time stepping where we have Bs n plus 1 x prime minus Bs n x prime divided by delta t is equal to minus R13 E L alpha 1 z prime. And similarly what we get for the second term is Bs n plus 1 y prime minus Bs n y prime is divided by delta t is equal to minus R23 E L alpha 1 z prime. So we will get the third equation in a very complicated form, because we are going to have the complex operator coming into play, and we will get an equation which is given by this complex term. We are not going to go much into the detail of this, because we just wanted to introduce this method. If you wanted to derive this individual equation step by step, we can give the references, but for now it's enough if you take it at the face value. So when we put alpha 1 and alpha 2 not equal to 0, the integration method becomes implicit, and every time step will be solving a linear equation which is given by this expression. So what we will get is Bn plus 1 is equal to minus delta t alpha 1 curl E n plus 1 plus f of b Bn comma En, where we have to define the f of E and f of b. We will define it in the next step. Similarly we get for the second expression the complex curl operator term coming into play, and the expression is given by this equation, and here we have to define f of E like we have to define f of b here. I think it's getting really crazy here with the expressions, and I wanted to be very clear. This is a very advanced method. It's not something that you can take it at the face value of the expressions that we are saying here. So for now it's enough if you understand that there is going to be a term that we call it as f of E and f of b, and these terms are going to be calculated based on the alpha terms that we have defined. And now you can think, here we are talking about two equations, and if you are in a simple 2D formulation you will get three equations, but basically we can combine these two equations into one equation, and that is what we do normally in second order wave equations, and that is what we are going to do also in this case. We can eliminate the Bn plus 1 term and obtain a second order equation in E of n plus 1, and this is something you can intuitively understand it from the wave equation point of view. Of course the terms here are too complicated. What we have here is an A operator operating on the E of n plus 1, the value that we need to compute. The moment we define the A operator, we can compute the value of the E of n plus 1 using this expression, and as you can see, this expression is both having the terms of alpha 1 and alpha 2, and when they are not equal to 0, it is going to be an implicit formulation. When they are going to be equal to 0, this entire term will disappear. So the value is going to depend on the alpha 1 and alpha 2 parameters that we have defined earlier, and it is going to depend on the complex curl term that we have defined, and we are having the right hand side like before, f of b of n comma e of n. So the beauty of this expression is the left hand side is going to be having terms which are e of n plus 1, and the a is nothing but the complex operator which is given by this expression within bracket, and on the right hand side we have the values which are purely dependent on the time step n. Here the f of b of n comma e of n is going to be given by this value. A is a SBD operator, and we discussed about positive definite operator when we discussed finite element method, and on the top of it, when the operator is also symmetric, it is called as symmetric positive definite, and A operator is a symmetric positive definite operator which follows from its structure and properties of the parameters that we have defined earlier. The reason for introducing mimetic method towards the end of our course module is it is really an advanced method, and one has to spend quite a lot of time really looking into the derivation of each and every parameters. We are going to give you references for this for advanced learners. This is not for any coursework. This is something only out of your curiosity that you wanted to learn this method. You are welcome to really look into those coursework. You are not going to be judged on your ability to understand all the individual derivations of the mimetic method. However, I would appreciate if you understand the overarching aspects of mimetic method, and that is going to be part of the discussions that we are going to summarize in the next slides. So the mimetic method is another way of looking at discrete structure. This is something you have to know. It is going to be another way of looking at discrete structure because it is going to give us a similar formulation to algebraic topological formulation. In that sense, there is going to be a lot of connection to algebraic topology. So what I want you to know is mimetic methods are very similar to the formulation of algebraic topology, and they are another way of looking at discrete structures. What I mean by discrete structures are nothing but discrete formulation of Maxwell equation, and when we model them on a structured Cartesian grid, they resemble the standard finite difference method. So those are the three important points that you should know. Apart from that, you should also know, unlike finite element method, the operators that we are going to define are going to be easily obtainable even on a very coarse grid, because in the finite element method we are forced to find or forced to construct the consistent adjoint operator, and it is going to be very challenging, whereas in a mimetic method it is very easy to do on any general grid. And due to that reason, the mimetic methods are going to give us an exact discrete counterpart of the partial differential equation we are modeling. More so, because of that, they are going to be free of the spurious solutions that are common to finite element methods. For example, in the case of finite element methods based on the nodal element methods, it is going to have a lot of spurious solutions. However, you can avoid that by going into edge element method, but still somehow some of the edge element methods can still lead to spurious solutions, whereas the mimetic method is completely free of spurious solutions or spurious modes. So that way it is going to be a better solution than finite element method. So those are the important aspects that I wanted to leave you with. You don't have to really know every detail of the mimetic method in order to go through this coursework. It is important for you to know there is something called as mimetic method, the discrete aspects which are going to mimic the continuous PDE that we are going to model. Secondly, we can take into account the discontinuous nature of the material parameters even on a rough grid, and also because of these properties they are going to be free of spurious solutions or spurious modes. So in that sense, these are the important aspect of the mimetic method based finite difference method. They can be very similar to the finite difference method when you are modeling them on a standard structured Cartesian grid, and they will have a similarity to algebraic topological method, which we dealt in much more detail in the previous modules. I wanted to end this module with this overarching summary. That are the aspects of the mimetic method that I wish every person who is taking this course should know. So I thank you for being part of this entire 12 weeks journey. We have learnt a lot during this entire 12 weeks. We have looked into very simple basic methods like finite difference method, finite element method, variational method, and we also looked into some of the advanced methods like finite volume method and algebraic topological methods. We have very briefly gave you in this module the overview of finite difference based mimetic methods. With that being said, there has been a lot of learning both for me teaching this course on an online platform like this. We have given our best in combining the theory with numerical experiments, and not only that, wherever possible we wanted you to come and experience the lab tours so that you can understand what are the devices we are modeling, because sometimes we have no clue about a waveguide, about antenna, about machines, transformers. So we wanted to break that barrier and we wanted to introduce you to the physical aspects of devices that we are modeling. So in that sense, we wanted to take those devices in our hands, feel them physically and understand them, their parts, their aspects, their functionalities, their important dimensions, so on and so forth. So that's what we did during the lab tours, and I feel that lab tours are going to be more and more valuable for people who are coming from outside electrical engineering. If you are coming from departments like physics, applied mathematics, it is going to be a very important element so that you can understand physically what are the devices, because some people would have never seen antennas. That is something we like to break, and that is the reason we have integrated wherever possible the lab tours into the coursework. And furthermore, we are in a course called computational electromagnetics. So we cannot do away with simulations. We have to do some simulations, and we have made sure simulations are integral part of this journey, and I am sure you have seen that. We have given you a lot of exercises, we have tested a lot of exercises during the course, and we also encouraged you to program your own codes and test it, and I am sure that you have discussed various aspects of the simulation during the last 12 weeks or so in the forum, and our teaching assistants were able to answer those questions much more supportively. And I personally hope that you have learned a lot about the basics of computational electromagnetics. Not only that, your perspectives and your understanding and your ability to model electromagnetic problems have changed. In that sense, I feel that we have given you a new foundation. We have given you a new basis to begin with your journey in the computational electromagnetic field. It doesn't end with this course, it has to continue. If you are an engineer working in a company, it's your daily routine. If you are a scientist working in labs, this is going to be your bread and butter. And also if you are a PhD student, this is going to support you in a very long way. So in that sense, we hope, I personally believe that this course has given you that perspective. I would like to hear about your opinions on the forum. With that being said, I wish you all the best for all your future projects, and also I wish you best of luck in the forthcoming examinations. Thank you.